Welcome to the deep dive. Today we're cutting through all the noise, all the hype, to get to the core of what is, well, probably the biggest shift in how we get around in a century.
You mean the electric vehicle revolution?
Exactly. The EV revolution.
And it is exciting, no doubt about it. But it can also be a bit confusing. EVs are suddenly everywhere, and they promise this amazing future with zero tailpipe emissions and these slick, high-tech dashboards.
But all that excitement can kind of mask some really fundamental questions
Okay.
about safety, about the economics of it all.
That's it. Are they actually safer? Are they truly greener and more economical, like right now, for the average person? That's what we're going to get into in this deep dive.
Yeah, exactly. So we've pulled together a ton of research to give you a shortcut really to being properly informed. We're talking about the high voltage systems, the complexities of crash scenarios, the long-term outlook.
Our mission today is really to understand the trade-offs. What are you gaining and what are you giving up? So we've broken this down into three key areas. First, we have to look at the unique inherent risks of an electric drivetrain, things that just don't apply to a normal car.
Okay.
Second, we'll get into the cost comparison. We'll pit EVs against, your standard internal combustion engine or ICE vehicles, and also against hydrogen fuel cell vehicles.
The other big contender.
And then finally, we'll look ahead. We'll talk about the game-changing innovations that are already starting to solve some of these current problems.
Okay, let's just jump right in then. Let's tackle the elephant in the room, the unique hazards. We're in segment 1, the risks of the electric drivetrain.
And these aren't just cars with, big AA batteries in them.
Not at all. We're talking about systems that are operating at several hundred volts.
That's the first critical point. The number one danger for anyone who has to interact with a damaged EV is that high voltage system.
We're talking about first responders, mechanics.
Anyone. And the potential is for severe, maybe even fatal electric shock. This isn't just a maintenance problem, it's a huge emergency response issue. Just imagine a car in a bad accident, wires are exposed, things are compromised.
And what happens when you add water to that equation? We see this all the time now with major floods.
Yeah, the research is pretty clear on this. Water submersion massively increases the risk of electrocution if those EV systems are damaged. It's a safety challenge that, a gasoline car just doesn't have.
But the thing that really grabs the headlines is fire.
Oh, absolutely. So, with EVs, you get rid of the risk of a gasoline fire, which is great.
Sure.
But you introduce a far, far more complex problem, and that's a thermal runaway.
Okay, that's a term we hear thrown around a lot.
Yeah.
But what does it actually mean when it happens?
In simple terms, it's like a chemical domino effect inside a battery cell. It's a self-sustaining chain reaction.
So if a battery gets punctured in a crash...
Exactly, or damaged in some other way. It starts to overheat. That heat then makes the cells next to it overheat, which releases more heat, which ignites more cells, and it just keeps going.
Until the whole thing fails.
Until the entire battery pack fails, often explosively. And the fire itself is just incredibly intense because it's being fueled by the lithium-ion chemicals inside.
And I've seen the reports on this. The practical side of fighting an EV fire sounds, frankly, staggering.
It is. Firefighters might need thousands and thousands of gallons of water, way more than for a normal car fire. And the scariest part is the fire can reignite.
Hours later.
Hours, sometimes even days after you think it's out. So the entire recovery process, just getting the car off the road after a crash, is fundamentally different and a lot more hazardous.
Wow. Okay, so beyond the fire itself, there are other consequences.
Right. You have to think about the environmental side. When these batteries burn, they release toxic fumes. And then there's the bigger picture. The sheer amount of lithium, cobalt, and nickel needed to make them in the first place.
All the mining and extraction.
Yes. And that brings up long-term environmental issues. We need a really robust global recycling system for these materials because they're not infinite and they're only found in a few places.
Okay, let's shift a little bit to the physical dynamics of the car itself. We always hear that the battery pack makes these cars really heavy. How does that play out in a crash?
Well, the current generation of EVs are, yes, significantly heavier than a similar-sized ICE car.
And that extra weight, that mass.
It translates directly into more kinetic energy, which means simply a greater impact force in a collision.
And this isn't just a theory, is it? I mean, we're seeing data now that suggests this weight difference, especially when an EV hits a lighter non-EV.
Right.
It could increase the injury risk for the people in that lighter car.
Absolutely. And it's not just other cars. That weight puts a lot of stress on our existing infrastructure.
Like what? Roads.
Roads, bridges, and especially older structures like parking garages, many of them have specific weight limits. So it raises this really important regulatory question. Do we actually need new crash safety standards or even new standards for our roads, specifically for these heavier vehicles?
That's a huge long-term challenge.
Hmm.
But there are also more immediate operational safety issues, like the fact that they're so quiet.
Correct. When you're driving slowly, say under 20 miles per hour, an EV can be almost silent.
And that engine noise is a cue that we all use, whether we realize it or not.
We do. Pedestrians, cyclists, and especially visually impaired individuals, they rely on that sound to judge how fast a car is coming and how far away it is. And with an EV, it's just not there.
Which is why they now have to make artificial sounds.
Exactly. It's now mandated. They have to install these sound systems that generate a specific kind of futuristic noise just to mitigate that risk.
And the last piece of this safety puzzle is one of the biggest hurdles to adoption. Emergency services. First responders, they face delays because they need special training, right?
They do. They need to know exactly where to find the high voltage cutoff cables, which are usually bright orange, thankfully.
Right.
And they need to know the precise location of the battery packs. If you're trying to cut someone out of a wreck, cutting it to the wrong spot could be fatal for you and for them.
And it doesn't stop there. The charging process itself has risks.
For sure. Public charging stations can malfunction, they can overheat and cause burns, and we've seen documented cases of improper home charging setups, people using the wrong wiring or extension cords causing electrical overloads and house fires.
So if safety introduces all these new costs and complications, the big question for you, the listener, becomes,
Right.
how do the economics actually stack up?
Yeah, let's pivot to that. This is segment 2, the competition for the future. We need to compare EVs, traditional ICE vehicles, and hydrogen.
Okay, so for the average driver, the EV versus IC calculation really comes down to two big things, doesn't it?
It does. It's the upfront price versus the long-term running costs.
And today, the reality is still that the initial purchase price of an EV is, well, it's often a lot higher than a comparable gasoline car.
It is higher. But, and this is a big but, that gap is shrinking. It's shrinking really fast because of improvements in manufacturing and, of course, government incentives.
Right.
And that higher initial cost is often balanced out by a huge reduction in what we call the total cost of ownership, or TCO.
So everything after you drive it off the lot.
Exactly. You completely eliminate oil changes, transmission fluid, all that regular engine maintenance. Electricity is way cheaper than gasoline per mile. And critically, regenerative braking.
Where the car recaptures energy when you slow down.
Right. That feature dramatically extends the life of your physical brake pads and rotors. You just don't replace them as often.
Okay, but on the performance side, EEs has some clear wins. That instant torque gives you that really fast acceleration. The ride is super smooth, it's quiet.
But ICE vehicles still have two major advantages for a lot of people.
Refueling.
Quick refueling, you're in and out in 5 minutes. And, just the psychological comfort of knowing you have a really long range and there's a gas station on every corner.
That's a big one. We also have to touch on depreciation. That used to be a huge fear for anyone buying an early EV.
Oh, it was a massive issue. They used to lose value so quickly because nobody was sure how long the batteries would last or how much they'd cost to replace.
But that's changing now.
It's really stabilizing. As the battery tech gets better and the warranties get longer, we're seeing resale values hold up much, much better. For some of the more popular models, they're actually holding their value extremely well. The whole financial picture is just becoming a lot clearer.
Okay, so that's EV versus gas. But now let's turn to the real long-term strategic battle.
The big one.
Battery electric vehicles versus hydrogen fuel cell vehicles, or FCVs. This is the fight for what sustainable transport will actually look like in the future.
And the technology is just fundamentally different. An EV, stores energy in a big battery that you charge from the grid.
Simple enough.
An FCV is more like a mobile power plant. It generates its own electricity on the fly by reacting hydrogen gas with oxygen from the air. And the only thing that comes out of the tailpipe is water vapor.
On the surface, that sounds perfect. Zero tailpipe emissions.
It sounds like the dream solution. But the problem isn't the tailpipe. It's the whole path to get to the tailpipe. The issue is efficiency.
You mean FCVs are less efficient than EVs?
Significantly less energy efficient. It all comes down to conversion losses. You lose energy when you make the hydrogen in the first place. You lose more energy compressing it and moving it around.
And then even more in the car itself.
And then you lose even more energy when the fuel cell in the vehicle converts it back into electricity. An EV By contrast, you just charge it directly and use that stored power with way fewer steps. That efficiency gap is a massive argument against FCVs.
And that green claim for FCVs, that really depends on where the hydrogen comes from, doesn't it?
Entirely. You have green hydrogen, which is made using renewable energy, and that's truly sustainable. But then you have gray hydrogen.
Which is most of it.
Which is most of it today, yeah.
Yeah.
And that's made using natural gas, which carries a pretty big carbon footprint of its own.
So, with all those downsides, why do FCVs still have any appeal?
2 words. Refueling, Steve.
Ah.
You can fill up an FCV with hydrogen in 3 to 5 minutes, just like a gasoline car. And they often have a longer range than many of the current EVs on the market. That's the key trade-off.
But the infrastructure is the killer.
Yeah.
Right? I mean, where do you even find a hydrogen station?
Exactly. The refueling network is extremely limited, it's incredibly expensive to build out, and it really only exists in a few specific places. EVs, on the other hand, they can leverage the entire existing electrical grid.
Plus, you can charge at home.
And you can charge at home. That gives them this monumental head start in terms of consumer adoption.
So when you look at the market right now,
EVs have clearly won the battle for passenger cars, at least for the foreseeable future. FCVs, though, they might still be the right solution for certain niche areas.
like what? Long-haul trucking.
Long-haul trucking, shipping, maybe heavy construction equipment. Places where you absolutely need short refueling times and really high energy density.
This is actually the perfect setup for our final segment. If EVs are the main trend, what innovations are happening right now to fix the problems we've been talking about? The range anxiety, the long charging times, the cost.
Yeah, let's talk about segment 3, where the road leads, advancements, and integration.
And it seems like it all comes back to the battery.
It's overwhelmingly focused on the battery. We're seeing some incredible research into higher energy density.
Which just means packing more power into the same amount of space.
Exactly. More power into a smaller, lighter battery. And that directly translates into longer range without making the car heavier, and it helps reduce the time you need to charge it back up.
But the real game changer that everyone is waiting for is the solid-state battery.
That's the one. It gets called the holy grail of EV development. And honestly,
It deserves the hype.
it really deserves the hype. Right now, lithium-ion batteries use a liquid electrolyte. It's flammable, and it degrades over time.
Okay.
Solid-state batteries replace that liquid with a solid material, like a ceramic or a polymer. And this promises just revolutionary improvements.
Like what specifically?
Well, first, far greater safety, because that solid electrolyte isn't flammable. Second, much, much faster charging. And third, a significantly longer lifespan for the battery itself. When this tech can be mass-produced, it will completely reset the cost and safety equation for EVs.
So beyond the battery itself, we have the charging infrastructure, which has to evolve.
Hmm.
Nobody wants to wait an hour at a public charger.
Nobody. So we're seeing huge investments in what's called ultra-fast DC charging networks. These are stations that can add, hundreds of miles of range in less than 15 minutes.
And what about wireless charging? Is that still a thing?
It is. It's less sexy, but maybe just as important. Wireless or inductive charging systems where you just park over a pad and the car starts charging automatically.
Yeah.
That technology is starting to gain a lot of traction, especially for commercial fleets.
So we have to talk about how all these EVs fit into the bigger energy picture. Because this is where the car stops being just a car.
And it becomes a player in the energy market.
Right. This is where vehicle-to-grid, or V2G technology, comes in.
It's a fascinating concept. Since most cars are just sitting parked 95% of the time, V2G allows the massive amount of stored energy in millions of EV batteries to be fed back into the grid.
So when demand is high, in the middle of a heat wave, for instance.
Exactly. It's a huge tool for utility companies, especially as they try to deal with renewables like solar and wind, where the supply is always fluctuating.
Wow.
EVs can act as this giant decentralized battery bank to help stabilize the entire grid.
But this brings up a really critical trade-off that you, the listener, have to consider.
It's a big one. While V2G is amazing for the grid, constantly discharging and recharging your car's battery, even just a little bit, it does shorten its overall lifespan.
So the economics of it have to make sense. The utility has to pay you enough for that power to make up for the extra wear and tear on your battery.
Precisely. That compensation model has to be worked out.
Ultimately, the future of this whole market is being pushed forward by these big global forces.
For sure. You have stricter emissions regulations, like what we're seeing in Europe and North America, that are basically forcing the industry to change.
And you can't ignore the geopolitics of it all.
No, the supply chain for the key battery materials, lithium, cobalt, nickel, it's very concentrated in just a few countries.
Yeah.
And that's leading to this huge policy push for domestic sourcing and manufacturing.
You combine all that with government incentives, with the rise of autonomous tech like robo-taxis.
And you just get this continuous drive for more scale and better affordability. It's what will ensure that EVs become the norm instead of, a novelty.
So after all that, what does this all mean? We finished our dive, and it really confirms this dual nature of the EV revolution. On one hand, you have this immense potential.
Lower running costs, zero tailpipe emissions.
But on the other hand, it's counterbalanced by these really critical inherent risks. Fire safety, vehicle weight, and the simple fact that the charging infrastructure isn't perfect yet.
And I think the most important thing to take away is that none of these problems are static. Every single limitation we've talked about today is being aggressively worked on by researchers.
From solid-state batteries solving the fire risk
To V2G technology solving the grid integration problem, the progress is incredibly fast.
So to bring this full circle, let's go back to that rivalry between hydrogen and electric. If you account for all the energy losses in making and moving hydrogen, the FCV's main advantage really just boils down to that 5-minute refueling time.
And that leaves a provocative thought for you to carry forward. It's this. If battery electric vehicles are just demonstrably more energy efficient than FCVs, and if V2G tech promises to turn the EV from just a drain on the grid into an actual asset, a source of revenue and stability, does the sheer technological and economic momentum of the BEV ecosystem make the whole argument for building a brand new hydrogen infrastructure just economically unviable, regardless of how fast you can refuel?
That's the multi-trillion-dollar question, and the answer will absolutely shape global transportation for decades to come.
Please like, subscribe, and get notified.